Dear students, let us we study today about geometrical and optical isomerism. In the earlier class, you have studied structural isomerism. Geometrical isomers have the same molecular formula, but they differ in the positions of the ligands around the central metal ion. If the ligands, if they are adjacent to one another, it is called cis isomer, and if the ligands, if they are across the one another or opposite to one another, they are called trans isomers, and this phenomenon is known as geometrical isomerism. In Latin, cis means the same and trans means across. Geometrical isomerism is not possible for complexes with coordination number 2 and 3 because in these arrangements all the positions are adjacent to one another. Geometrical isomerism is found in the complexes of coordination number 4 and 6 very commonly. Complexes with coordination number 4 exhibit either tetrahedral or square planar geometry. Cis-trans isomerism is not possible in case of tetrahedral complexes because all the 4 ligands are adjacent to one another. However, it is very common in square planar complexes. Cis-trans isomerism is found in the square planar complexes of the type M(A2)(B2), M(A2)(BC) and M(AB) twice, where AB is a bidentate ligand. In case of MABCD type of a complex, 3 isomeric forms are present. Cis-trans isomerism cannot occur in the square planar complexes of the type MA4, MA3B or MAB3. Here A and B are monodentate ligands. Let us we study the square planar complexes of the type MA2B2. The example for this is the diamine dichloroplatinum 2, and another example is diamine dinitritoN palladium 2. In case of cis isomer, both chloro and ammonia ligands are adjacent to each other in case of cis isomer. In case of trans isomer, the chloro and ammonia ligands are opposite to each other. Coming to the MA2BC type complexes. This type of complex contains 3 different types of ligands A, B and C. Example for this is the amine chloro dipyridine platinum 2 complex. Students, you have to remember the charge will not show the valency of platinum. Here the charge in this complex, pyridine and ammonia are neutral ligands. Chlorine is a negatively charged ligand. Therefore, the chlorine valency is -1. Platinum exhibits +2. +2 -1, the charge remained is +1. That +1 charge is a charge of the complex ion. But this charge is not the valency of the central metal ion. This should be remembered. Here also I have shown, in case of the cis isomer, the pyridine are adjacent to each other, and in case of trans isomer, the two pyridines are opposite to each other. In AB2 type complexes, here AB is a bidentate ligand. So the example for this is an amino acid called the glycine. Glycine is a bidentate ligand where the nitrogen of the amino group and oxygen of the carboxylate group both are involved in the coordination. In case of the cis isomer, both the nitrogen are adjacent to each other, and in case of trans isomer, both the nitrogen are opposite to each other. Coming to the MABCD type of the square planar complexes, where A, B, C and D are monodentate ligands. They exhibit 3 isomers. The structure of these isomers can be written by fixing the position of one of the ligand and placing the other ligands B, C and D trans to it. So if you see below the structure, I have written a ligand A on the left hand top corner in all the 3 structures. Now opposite to A in all the 3, I have written in one case B, in another case C, in another case D. If in the first ligand, the first complex, AB is trans to it, then the CD will be the other part. In the second case, AC is trans to it and BD are the other 2 parts. Similarly, in the third case, A and D are trans to it, so that B and C are opposite to each other. Geometrical isomerism in the complexes of coordination number 6. Complexes with coordination number 6 exhibit octahedral geometry. Octahedral complexes of MA6 type, MA5B, MAA3, where AA is a bidentate ligand, give only single geometrical isomer. That is, complexes of this type do not show cis-trans isomerism. Octahedral complexes of the type MA4B2, MA3B3, MA2B2C2, MAA twice A2, MAB AA twice, MAA2B2, MAB thrice exhibit cis-trans isomerism or geometrical isomerism. In case of MABCDEF type of complex, theoretically 15 geometrical isomers are possible. Let us take an example of MA4B2 type of the complex. So it is the tetramine dichloro cobalt 3 ion. In cis position in the cis complex, the ammonia and the chloro ligands are adjacent to each other. In the trans isomer, these are opposite to each other. Coming to the MA3B3 type of the complex. In MA3B3 type, the example is triamine trichloro cobalt 3. It is a neutral complex. In cis form, the 2Cl and 2NH3 are adjacent to each other, and in case of trans form, the 2Cl and 2 ammonia are opposite to each other. octahedral complexes of this type also exist in two geometrical isomers, namely facial or FAC isomer and meridional or MER isomer. When the three ligands of the same donor atoms are on the same triangular face of the octahedron, the compound is called facial or FAC isomer. It is also called 1,2,3 isomer because of the same donor atoms at these positions. When the three ligands of same donor atoms are on the same equatorial plane of the octahedron, the compound is called meridional or MER isomer. It is also called 1,2,6 isomer because of the same donor atoms at these positions. Let us take an example of the complex of the type Ma2B2C2 type. So here they exhibit totally 5 geometrical isomers. Out of these, only 3 have been synthesized in the laboratory. The example is diamine, dichloro, dipyridine, platinum 4 ion. I have shown all the structures of these complex. Now let us take MAA2A2 type of the complex, where AA is the symmetrical bidentate ligand in which A and A are two identical coordinating donor atoms. So dichloro, bisethylene, diamine, cobalt 3 ion. In this case, the two chloroligands are adjacent to each other in cis isomer, and in trans isomer they are opposite to each other. So in case of the MAA2AB type of the complex, the two ligands A and B are the chloro and ammonia. These are adjacent to each other in cis form, and chloro and ammonia, they are opposite to each other in trans form. MAA2B2 type of the complex, the chloro and ammonia are they are opposite to each other, but the two ammonia group are cis to each other, and two chloro ligands are cis to each other. In case of the trans case, the two ammonia and are trans to each other. Lastly, the MAB3 type of the complex. AB is an unsymmetrical bidentate ligand in which A and B are two different coordinating donor atoms. The example is the triglycine chromium 3. In case of the cis isomer, so all the three nitrogen are adjacent to each other and also the oxygen, and in case of the trans, they are opposite to each other. Coming to the optical isomerism. Before to know about the optical isomerism, let us study some of the fundamental aspects of this optical activity. The ordinary light, it travels in all the directions. When this light is passed through a Nicol prism, then we get a light traveling only in one direction. This light is called plane polarized light. The plane polarized light travels in one direction. When this light is passed through the solutions of some of the complex compounds, then these complex compounds, they rotate either to the left or to the right. If it rotates to the left, then those complexes are levorotatory compounds, and if they rotate to the right, then those complexes are called dextrorotatory compounds. The condition for the optical activity. When a compound exhibits this optical activity, the conditions are: number 1, the complexes of D and L isomers have same physical and chemical properties. They differ only in optical property. D and L forms are mirror images to each other, just as left hand is the mirror image of the right hand. Thus, D and L forms can be superimposed on each other, hence they are called enantiomers. Thus, optical isomerism is now often referred to as enantiomerism. The third condition is, since D and L forms are mirror images, therefore their structures are not superimposable. D and L forms of optical active compounds must not have a plane of symmetry. The fifth one, the optical isomer, which is not capable of rotating the plane polarized light, is called racemic mixture. The racemic substance is composed of 50% the D form and 50% L form of the optical isomers. Hence, these are optically inactive. Optical activity exists in asymmetric molecules. So, you have studied this optical activity in organic compounds, where a carbon atom containing 4 different atoms or groups, which is also called asymmetric carbon atom, where you come across optical activity. Similarly, even in co-ordination compounds also. Square planar complexes with co-ordination number 4 do not exhibit optical activity because they possess a plane of symmetry. In tetrahedral complexes of the type MABCD, analogous to tetrahedral carbon atom, should exhibit optical activity. However, it has not been possible to isolate D and L form of optical isomers. Tetrahedral complexes of beryllium, boron, copper 2, zinc 2, etc. containing unsymmetrical ligands have been resolved into optical isomers. Here, the geometrical isomers are possible with geometrical isomers are possible in co-ordination number 4 of the square planar complexes, but optical isomers are not possible in case of square planar complexes. However, it is reverse even in tetrahedral also. One such example showing the complex, the beryllium, exhibiting optical activity. Here the structure looks the same. It is not the same. In the first structure, the left side of the ligand is on the x-axis and the right side it is on the y-axis. That means they are perpendicular to each other. If it is on the x-axis, the left ligand, in another complex, it is on the y-axis and vice versa. Tetrahedral complexes of Ma4 and Ma3b type are not able to show optical isomerism because all the possible arrangements of the ligands around the central metal ion are exactly equivalent. Now let us study optical isomerism in octahedral complexes. Both cis and trans isomers of Ma4b2 and FAC and MER isomers of Ma3b3 are optically inactive because of the presence of plane of symmetry. The cis isomer of Ma2b2c2 type show optical isomerism. The diagram shows the first condition is if you take the mirror image, these two are the mirror images. So mirror image means you take the first compound, rotate to 180 degree and fix it on the second. So then it must be the same as the second compound. Then it is called the mirror image. Now another, you take the first, the object, and you keep in the same way on the second. Then the first and second will not be the same. And this we call non-superimposable. So the condition must be the two isomers are mirror images and they must be non-superimposable. Now MABCDEF type of complex exhibit optical isomerism, where I have shown the diagram. Here the bromine and iodine are perpendicular to the plane, and when it is rotated to 180 degree, when it is rotated to, that is the rotation must be only the what you can say the square planar part. When it is rotated to 180 degree centigrade, we get the another one which is non-superimposable on the first. Therefore, the optical activity is possible in this case. Complexes of the type MAA3, where AA is a bidentate ligand, exhibit optical isomerism. Now, I have shown a diagram here. Here, both cis and trans forms of this type of complex exhibit optical isomerism. Cis form of MAA2A2 type of the complex exhibit optical isomerism. However, its trans isomer does not, due to the presence of plane of symmetry. I have shown the diagram. See, the cis D isomer and cis L isomer. These two are mirror images. Whereas the trans isomer, if you take the mirror image becomes the image of the first one only. Both are superimposable. Hence, the trans isomer forms called the mesoform, and this mesoform is optically inactive. Cis isomer of MAA2AB type of the complex exhibit optical isomerism. However, its trans isomer does not, due to the presence of the plane of symmetry. So go through the diagram and you can understand the structures. So in the first two are unsymmetrical forms, and the third one is the symmetrical form. It is a transform and it is also called the mesoform, optically inactive. Cis isomer of MAA A2B2 complex exhibit optical isomer. However, its trans isomer does not due to the presence of plane of symmetry. So go through the diagram. It is similar to the previous one. Here I have shown the structures of the cis-trans isomerism in square planar complexes. These diagrams gives still more better ideas for you to understand this concept. Here I have shown the types of the square planar complexes with the colored figures, from which you can understand much more about the cis and the trans form. In this slide, I have shown a plane polarized light, that is optical activity. So if you take a normal light, the normal light travels in all the directions. So when you pass this through the polarizing filter or a Nicol prism, both are the different types, but they do the same, what you can say, the things. So when they are passed through the polarizing filter, the outcoming light is having the traveling only in one direction. That is called polarized light. When the polarized light is passed through optically active solution, then the polarized light, it rotates through some angles, either to the left or the right, and if it rotates to the left, it is called levorotatory compound. If it rotates to the right, it is called dextrorotatory compound. And the slide gives a clear picture of optical activity. In this, I have shown various complexes showing the geometrical isomerism, both cis and trans isomerism as well as optical isomerism. In the previous slide, I have also shown the FAC and MER isomers. Go through the structure properly, from where you can understand the meaning of FAC and MER isomer. This slide gives the geometrical isomers and optical isomers. Here I have shown a mirror image, how that mirror image it looks. Students, go through the cis-trans isomerism as well as optical isomerism, and practice these structures. Thank you.